Welcome. We are conducting a structured analysis of foundational text excerpts concerning quantum computing. We'll look at the core concepts, the algorithms, and the infrastructure needed to understand this field.
The source material provides a comprehensive technical framework. It moves from the mathematical underpinnings right through to current hardware implementations.
Our goal today is to extract the critical, high-impact insights from this material. We'll prioritize the connections between theory and, well, engineering reality.
Please note that this detailed knowledge extraction is generated by an artificial intelligence system. This helps ensure impartial and comprehensive coverage of the provided source material for you, our technical audience.
We will proceed with detailed precision, maintaining a professional and deliberate pace throughout our discussion.
We've actually reorganized the content thematically. This goes beyond a simple sequential chapter review to help you absorb the most crucial concepts more efficiently.
Okay, let us begin then by establishing the fundamental physics that makes quantum computation possible. This involves key concepts, primarily from chapters 1 and 3 of the text: superposition, entanglement, and the basic building block, the qubit.
A quantum computer is distinct precisely because it actively exploits quantum mechanical properties. Now, superposition allows a system to exist in multiple states simultaneously.
But you mentioned entanglement is where the real power lies.
That's correct. Entanglement is a specific kind of superposition where information is encoded in the correlation between particles, not just locally within one particle.
That's the spooky action at a distance phenomenon.
Exactly. It underpins the non-classical behavior that gives quantum computers their potential advantage.
And the process of getting information out, the measurement, that's governed by the Born rule, correct?
Yeah.
From section 1.2.
Yes. While a quantum state's amplitude can be a complex number, the probability of measuring that specific state is determined by the squared modulus of that complex amplitude.
Which always results in a real number between 0 and 1. Probability.
Precisely. It's the mathematical bridge, you could say, between the complex multidimensional quantum world and the single real outcome we observe in an experiment.
So how does the state itself change over time before measurement?
That's governed by Schrödinger's equation. Section 1.3 covers this. It features the reduced Planck constant, denoted daughter, and the Hamiltonian operator, head.
And the Hamiltonian hala represents the total energy of the system.
Yes, kinetic plus potential energy. This equation dictates how the qubit state evolves. A key example application mentioned is the quantum harmonic oscillator, which is relevant for things like molecular simulation.
Now, if the physics dictates what quantum state is, section 1.4 introduces Landauer's limit. This seems to dictate what computation costs in terms of energy.
That's a good way to put it. Logical irreversibility. Think of a classical OR gate, where you can't know the input just from the output. Well, that necessitates physical irreversibility.
Which increases the system's entropy and dissipates heat, according to thermodynamics.
Exactly. Quantum computation, on the other hand, leverages unitary operators. These are inherently reversible, which helps minimize this fundamental energy cost associated with erasing information.
Let's connect that to the qubit itself, defined in Chapter 3. A two-level system in a two-dimensional complex Hilbert space, Math BBC 22.
Correct. And manipulating this qubit requires quantum operators. For the gate-based systems we often discuss, these operators must be unitary.
Unitary meaning they preserve the vector norm, which physically means probability is conserved throughout the computation.
Precisely. And if we want to measure something specific, an observable quantity, the operator corresponding to that measurement must be Hermitian.
Why Hermitian?
It's a strict mathematical requirement. Hermitian operators guarantee that their eigenvalues, the possible results of the measurement, are always real numbers. This aligns with the real-world outcomes we observe.
This leads us nicely into the foundational gates mentioned in Chapter 3. The Hadamard gate H seems crucial.
It is absolutely fundamental. The Hadamard takes a definite basis state, like zero angle or $1 angle, and puts it into an equal superposition. For instance, creating the state dr angle plus 1 angle divided by the square root of 2.
And for building more complex circuits, we need universal gate sets. The text highlights CNOT, TH as one such universal set.
Yes, that's a standard one. Universality means you can approximate any possible quantum computation using only gates from that set.
But there's a nuance here with the Gotzman-Mill theorem, also mentioned in Chapter 3.
Yes, that's important. The theorem states that if your circuit only uses gates from the Clifford group, that's CNOT, SH, then the entire computation can actually be simulated efficiently on a classical computer.
So the inclusion of a non-Clifford gate, like the T-gate, is what's essential for achieving true quantum computational advantage. The kind of advantage that separates the complexity class BQP from P.
Exactly. It seems like a small mathematical addition, but that non-Clifford gate is what unlocks the potential power. And the Solovay-Kitaev theorem assures us we can approximate any desired gate efficiently using sequences from a universal set.
Let's pivot now from the physics foundations to the theoretical promise, the algorithms that actually define this quantum advantage. This draws from chapters 2, 4, 7, and 8. What was the key takeaway from the early history beyond Feynman's initial ideas?
I think the biggest shift was the concrete realization that quantum computers could solve specific problems exponentially faster than their classical counterparts.
Like the Deutsch-Jozsa and Bernstein-Vazirani algorithms.
Precisely. While perhaps more academic, they were the first to demonstrate this quantum classical separation. DJ showed a deterministic speedup, and BV showed a non-deterministic speedup for a particular problem.
The BV algorithm solved a secret function problem in constant time, O1, which classically takes linear time, ON.
That's correct. A clear separation, even allowing for small errors.
Then came the major breakthroughs in the mid-90s, Shor's and Grover's algorithms. Section 2.2 highlights these.
Shor's algorithm, well, that really changed the landscape. It tackles the problem of factoring large numbers, which is the basis for security in systems like RSA.
It does this by transforming the factoring problem into finding the period of a specific modular function, PUCO x equals xp mod, and $9.
Yes, and the exponential speedup comes from using two core quantum subroutines: quantum phase estimation, or QPE, and the inverse quantum Fourier transform, the inverse QFT.
So Shor's gives exponential speedup for that very structured problem. What about Grover's? Section 8.7 discusses it.
Grover's algorithm offers a Dubin-kind advantage. It provides a quadratic speedup, QORIX, for unstructured search problems.
Searching an unsorted database, essentially.
Exactly. While quadratic speedup isn't exponential, the sheer breadth of applications for search makes Grover's algorithm incredibly significant and practical.
This inherent potential for speedup is why Chapter 4 delves into complexity theory, defining the relevant classes.
Correct. We have the classical classes P, NP, PS space, BPP, and then the quantum counterparts: BQP, bounded error quantum polynomial time, and EQP, exact quantum polynomial time.
And BQP is the key class here. It contains problems believed to be intractable classically, like factoring, but solvable efficiently on a quantum computer.
That's the central idea. It's important to note, though, that BQP doesn't contain all of NP. Quantum computers don't magically solve all hard problems, only those with specific structures, like periodicity, that algorithms like Shor's can exploit.
The major theoretical consequence discussed in Section 4.4 is the challenge this poses to the Extended Church Turing thesis, the ECTT.
Yes, the ECTT suggests that any algorithmic process can be simulated efficiently by a classical probabilistic Turing machine.
But quantum computation, by demonstrating potential exponential speedups for problems like factoring, challenges this thesis.
It does. This leads to the currently standing hypothesis, the Quantum Extended Church Turing thesis, or QECTT. This theoretical tension, this potential computational separation, is really what fuels the entire field.
Before we get to building the hardware, Chapter 7 offers some fascinating insights into quantum information transfer itself. Teleportation, for instance.
Quantum teleportation is a beautiful example. It allows the transfer of an unknown quantum state, say wrangle, from one location to another using a pre-shared entangled pair, an EPR pair, and the transmission of just two classical bits.
So it shows quantum information isn't copied in the classical sense, it's fundamentally relocated.
Exactly. And Section 7.3 discusses the Bell inequality test game. This really highlights the power of entanglement.
Classically, two separated parties playing this game, using only shared classical information or strategies, can win at most 75% of the time.
But if they share an entangled quantum state and use a quantum strategy, they can consistently achieve a higher winning probability, around 85% specifically at Calum.
That higher correlation, impossible classically, is a direct consequence of entanglement.
Indeed. It's that non-classical correlation that ultimately fuels the potential for quantum speedups in algorithms.
Okay, let's transition now to the practical side. Building the machines and actually running these algorithms. This draws from chapters 5, 6, 9, and 10.
To assess quantum hardware, Section 5.1 refers back to DiVincenzo's criteria, which we touched on briefly.
Right, the checklist. Scalable qubits, the ability to initialize them, long coherence times, a universal set of quantum gates, and reliable measurement capability. How do the current leading platforms measure up?
Well, the hardware landscape is quite diverse, as detailed in Chapter 5. Superconducting qubits, used by companies like Google, IBM, and Rigetti, are a prominent approach.
These require extreme cooling, though, down below 10 millikelvin.
They do, but they offer potential advantages in fabrication and integration. Then you have trapped ion systems.
These use ionized atoms held by electromagnetic fields.
Correct. They boast very high coherence times and often don't need the same level of extreme cooling. Architectures like the quantum charge coupled device, or QCCD, are being pursued here.
Chapter 5 also mentions other platforms, like neutral atom systems. Section 5.2 discusses these, using configurations like IOGS. They show promise, but face scaling challenges.
And photonics, Section 5.5, which uses photons, particles of light, as qubits. This is appealing for chip-scale integration and room temperature operation in some cases, but photon loss remains a significant source of error.
Regardless of the specific hardware, we need software to program it. Chapter 6 introduces the quantum computing stack.
Yes, from the physical hardware up to the algorithms. Quantum programming languages, QPLs, allow interaction with development libraries like Qiskit, Cirq, and QStack.
The text uses Cirq, Google's library, for many examples, and Section 6.1 discusses QC simulators.
Simulators run on classical computers, vital for testing code, but they face the inherent exponential explosion. Storing the state of just new op-eds requires 200 complex numbers,
which quickly becomes unmanageable. Simulating 50 qubits needs around a petabyte of classical memory.
Exactly. This highlights the fundamental boundary classical simulation faces and motivates the push towards building actual quantum hardware. State vector simulation methods try to optimize this, but the exponential scaling remains.
This complexity barrier is precisely why demonstrating quantum supremacy, discussed in Section 10.2, is such a significant milestone.
Quantum supremacy means experimentally demonstrating a quantum computer solving a specific, perhaps contrived problem that is provably intractable for even the most powerful classical supercomputers.
Random circuit sampling is often used as a candidate problem for this kind of demonstration.
Yes, because classically simulating the output probability distribution of a sufficiently large, complex, random quantum circuit becomes exponentially difficult. Achieving this refutes the extended Church-Turing thesis experimentally.
Now, moving to the methods in Chapter 9, much current research, especially in this NISQ noisy intermediate-scale quantum era, focuses on hybrid quantum classical algorithms.
That's right. These algorithms leverage both quantum processors for tasks they excel at and classical computers for optimization or control. The variational quantum eigensolver, VQE, is a prime example. Section 9.1 covers it.
VQE is used to find the ground state energy of a molecule's Hamiltonian, for instance. It uses a quantum circuit with tunable parameters.
Then uses a classical optimizer to adjust those parameters, iteratively minimizing the measured energy expectation value angle.
Similarly, Section 9.3 discusses the Quantum Approximate Optimization Algorithm, QAOA.
QAOA targets combinatorial optimization problems, like the max cut problem on a graph. It also uses a parameterized quantum circuit and a classical optimization loop to find good approximate solutions.
These hybrid approaches seem essential while we deal with noisy, imperfect qubits. Chapter 9 also covers quantum machine learning, QML.
Yes, Section 9.4. This involves encoding classical data into quantum states, processing it with a quantum neural network circuit, and then measuring a readout qubit.
There's also the concept of dequantization mentioned here.
That's an interesting point. It refers to situations where classical algorithms, sometimes inspired by quantum ideas, manage to achieve performance competitive with proposed quantum algorithms for certain tasks, like recommendation systems. It highlights the ongoing race between classical and quantum approaches.
Let's touch upon some more core quantum subroutines. Quantum phase estimation, QPE, from Section 9.5.
QPE is crucial. It's a key component within Shor's algorithm. It efficiently estimates the phase, which corresponds to an eigenvalue associated with an eigenstate of a given unitary operator.
Provided you can prepare that eigenstate. Then there's the HHL algorithm in Section 9.6.
Named after Harrow, Hasidim, and Lloyd. HHL offers an exponential speedup for solving systems of linear equations, MMath-BFD-SB.
But with important caveats, right? The matrix S$ needs to be sparse, and the solution vector MathBFD is encoded in the amplitudes of a quantum state, 6 Wrangle dollars. Extracting the full classical vector can negate the speedup.
That's correct. The speedup is conditional, but potentially powerful for specific applications where you only need certain properties of the solution vector.
Chapter 9 also briefly mentions things like quantum random number generators, QRNGs.
which leverage the inherent randomness of quantum measurement, like measuring a qubit put through a Hadamard gate to produce truly unpredictable numbers.
And quantum walks?
Quantum walks, section 9.8, are the quantum analog of classical random walks. They can propagate quadratically faster due to quantum interference effects, offering potential speedups for certain search and sampling problems.
And finally, section 9.9 introduces the quantum singular value transform, QSVT. This sounds like a unifying framework.
It is quite remarkable. QSVT provides a general method for applying polynomial functions to the singular values of matrices that are block encoded within larger unitary operators. It turns out many major quantum algorithms factoring, search, HHL simulation can be expressed within this QSVT framework.
That suggests a deeper underlying structure connecting these seemingly disparate algorithms.
Precisely. It's a very active area of research.
Now, underpinning the long-term feasibility of all this is quantum error correction, QEC, addressed in section 10.3. Quantum states are incredibly fragile.
They are highly susceptible to noise from the environment, causing decoherence and errors. QEC is absolutely necessary for building fault-tolerant quantum computers.
The text uses the simple 3-qubit repetition code as a motivating example.
Yes, you encode one logical qubit into 3 physical qubits. For example, the logical state 0 of overline wrangle becomes the physical state vert $1,000 wrangle. This allows you to detect and correct a single bit flip error on any one of the 3 physical qubits.
But the overhead is significant. Here, 3 physical qubits for 1 logical qubit. The notation DeLau bracket NT DEDRE bracket captures this.
Correct. The null is the number of physical qubits, 2 quarterly is the number of logical qubits encoded, and dollars is the code distance, the minimum number of physical errors needed to cause an uncorrectable logical error. Larger distance means better protection, but typically requires more physical qubits.
This need for massive physical qubit overhead is a major engineering challenge for scaling up current hardware platforms.
It certainly is. The standard mathematical framework for designing and analyzing these codes is the stabilizer formalism, also introduced in Chapter 10. A protected state is one that remains unchanged. It's stabilized by a specific set of operators called the stabilizer generators.
Okay, finally, let's briefly cover the mathematical toolkit presented across chapters 11 through 14. For our technical audience, we won't rehash basic linear algebra. Instead, let's focus on the key mathematical structures and constraints specific to quantum mechanics.
Agreed. The first absolutely essential element, discussed in section 11.3, is the necessity of complex numbers. Quantum states have amplitudes that are complex numbers, a plus be a null.
This leads directly to the definition of the inner product in complex vector spaces. The conjugate symmetry property, overline, overline, overline VU, is critical.
It is. It ensures that the inner product of a vector with itself, a Langle-psi wrangle, which represents the squared length or norm, is always a non-negative real number. This connects directly to probability.
Second, the mathematical container for quantum states is defined in section 12.8 as a Hilbert space.
Specifically, a complete vector space over the complex numbers math BBC equipped with a complete inner product. The state space for a single qubit, as confirmed in section 12.9, is a two-dimensional complex Hilbert space, math BBC 2.
Third, we rely heavily on 2 specific types of operators or matrices. Permission operators, section 12.5.
As we discussed earlier, these represent physical observables. Their defining property is that they always have real eigenvalues, ensuring our measurement outcomes correspond to real physical quantities.
And fourth, unitary operators, section 12.6. These represent the evolution of a closed quantum system, including our quantum gates.
Their defining property is that they preserve the inner product and thus the norm or length of state vectors. MathBFE wrangle. This mathematically guarantees that total probability remains 1 throughout the computation.
These fundamental concepts are elegantly captured using Dirac notation or bracket notation, which is formalized in chapter 14.
Yes, a column vector state is represented by a ket. Its conjugate transpose, a row vector, is represented by a bra.
This notation simplifies many common operations. Superposition is just a linear combination alpha wrangle plus beta 1 wrangle. The inner product, yielding a scalar, is Langle UV wrangle.
And the outer product, which yields a matrix or operator, is written as Weiler wrangle v dollar. Tensor products for multi-qubit systems are also concise, like DL wrangle times wrangle becoming simply dearly dollar regal.
The text then concludes in chapter 15 with a very useful reference table.
Indeed. It lists key quantum operators, like the Pauli matrices XYZ, Hadamard H, various controlled gates, CNOT, CZ, phase gates, and provides their matrix representations and circuit symbols. An invaluable resource for practical implementation.
So this analysis has synthesized quite a substantial technical framework. We've moved from foundational physics and mathematics through to algorithms, hardware realities, and error correction needs.
The sheer breadth of the material covered in the source text, from the complexity theory implications challenging the ECTT, right down to the rigorous definition of Hilbert spaces and the necessity of QEC, really demonstrates the deeply interdisciplinary nature of quantum computing.
We absolutely recommend that you read the full text provided. It offers much greater depth, particularly with the practical code examples interwoven throughout the chapters.
That practical aspect is crucial for truly understanding how these concepts translate into actual quantum programs.
Before we conclude, here's a final provocative thought for you to consider, building on our discussion. If the quantum extended Church-Turing thesis ultimately holds true, meaning a quantum computer can simulate any physical process efficiently, does the path to truly powerful quantum computation rely less on simply building ever larger physical devices, and perhaps more on discovering unifying theoretical frameworks, like QSVT, to optimize and generalize the algorithms we apply to those devices? Something to think about.
We encourage all friends of the show to subscribe for more explorations like this one. Please do check the links in the description for additional resources related to the topics we've discussed today.
Thank you for joining us for this session.
We wish you a great day.